Good evening, everybody. So, in this lecture, we discuss some of the problems on how to determine the laminar boundary layer thickness, shear stress, and drag force. Similarly, how to determine the turbulent boundary layer thickness, shear stress, and the drag force. And if suppose on the plate up to certain distance laminar boundary layer is there, and beyond that turbulent boundary layer is there, then how to determine the drag force? So these are the three types of questions we have in this growth of boundary layer over a flat plate. So let us do these three problems now. Now topic is problems on boundary layer theory. There are the types of problems are if the boundary layer is laminar boundary layer, then determine thickness, shear stress at any point, then drag force. Third, the second type of problem is if the boundary layer is turbulent boundary layer, then determine thickness, shear stress, drag force. Third problem is if the boundary layer at leading edge is laminar boundary layer and converted into turbulent boundary layer, then we don't need to discuss about thickness because wherever you are finding out the thickness, use that relevant formula for the whether laminar boundary layer or turbulent boundary layer and calculate. Even the shear stress at a point also, depending on where you are calculating the shear stress, use either laminar boundary layer or turbulent boundary layer depending upon the boundary layer. But only thing is, because the drag force is calculated based on for the entire plate we do it, and on the plate some distance laminar boundary layer and some distance turbulent boundary layer is there. That is where the problem comes. And in that case, only the problem that we will do it is the drag force calculation. So these are the three problems we have in this particular topic. I take one after the other quickly and let us do it that problems. First problem, a flat plate 2 meters width and length L is kept parallel to a uniform stream A is equal to 0.15 Stokes kinematic viscosity at a velocity of 20 kilometers per hour. It is desired to have laminar boundary layer he has given only on the plate. Calculate the maximum length of the plate in meters. Right? So what is our thing? Only laminar boundary layer. Only if laminar boundary layer is formed. Then how to calculate? First thing is if you want to calculate the what is the maximum length of the plate. We know laminar boundary layer exists up to a Reynolds number 5 into 10 to the power of 5. That is first thing. So if that is the case, what is the thing? REL, the Reynolds number should be equal to 5 into 10 to the power of 5 maximum, because he has asked maximum length, otherwise it should be less than or equal to. Maximum length means we go for the maximum. And what is Reynolds number? Reynolds number is equal to VL by nu is equal to 5 into 10 to the power of 5. Then what is V he has given? He has given 20 kilometers per hour. That means 20 into 1000. If I put it, I am converting into meters per hour to per second. Per hour to per minute 60. Per minute to per second 60. So if I simplify this, it is going to be 200 by 36 meters per second. Then what is kinematic viscosity? He has given 0.15 Stokes. So that means 0.15 into 10 to the power of minus 4 meter square per second. So now if I substitute, that is 200 by 36 is the velocity into L is unknown, which we determine. Then this is 0.15 into 10 to the power of minus 4 is equal to 5 into 10 to the power of 5. Therefore, if you calculate L, L is equal to 1.35 meters. So that is the solution. So let us go to the second problem. A thin plate measuring 75 centimeters by 25 centimeters is exposed parallel to a stream of water of uniform velocity 1.2 meters per second. If the kinematic viscosity is 1.1 centistokes, determine the maximum boundary layer thickness during stress at trailing edge and drag on both sides of the plate. Now if I take it, they have given nu is equal to 1.1 centistokes. 1.1 into 10 to the power of minus 2 strokes is equal to 1.1 into 10 to the power of minus 2 into 10 to the power of minus 4 meters square per second. So finally it is 1.1 into 10 to the power of minus 6 meters square per second. This is the first one. Once the first one is over, then next one what we have to do? Reynolds number. Reynolds number at the end of the plate, that is why I wrote L, is equal to V into L by nu. So what is velocity he has given? He has given the velocity as if I see 1.2 meters per second. V is equal to 1.2 meters per second. This also he has given. So 1.2 into L is how much he has given? 0.75 divided by nu is equal to how much? 1.1 into 10 to the power of minus 6. So finally all this will be how much actually? 2,72,700, which is less than 5 into 10 to the power of 5. That means the boundary layer formed is laminar boundary layer. Confirm. Then afterwards, now A, what is the thickness? He asked maximum thickness, where he asked at the trailing edge. So delta by x is equal to, our rule is 4.91 divided by Rex. As x is equal to L, Rex is equal to Rel, because at trailing edge. Therefore, delta by L is equal to 4.91 divided by Rel. So therefore, delta is equal to 4.91 into L divided by root Rel. Here some people will write instead of 4.915 also. There is nothing wrong even if you put 5 also. Please remember, this you can write 5 also, no issues. So if you put it 4.91 into L is equal to how much is the length? 0.75 divided by root of Rel is 2,72,700. So thickness is equal to how much it has come? 2.35 into 10 to the power of minus 3 meters. It is equal to 2.35 mm. This will be the order of the thickness. Then coming to the B. B is what actually? The shear stress. And shear stress where he want? At the trailing edge. At a trailing edge. That is at x is equal to L. So therefore, so what is the formula for shear stress? It is equal to CD star into half rho V square. What is CD star? Is equal to 0.664 divided by root of Rex. But in this problem, we want at the trailing edge, so naturally it will be Rel. So 0.664 divided by root of 2,72,700. This is our next thing. So this is one point. Once this is obtained, so put it in that. Then tau naught is equal to then 0.664 divided by root of 2,72,700 into half. into basically, because he has given it as water. So water mass density is 1000 kg per meter cube into what he has given. Other one he has given is how much? The velocity is 1.2 whole square by 2. So this answer will be 0.915 Newton per meter square. This is the next answer. Drag force on one side of the plate. On one side of the plate. What is the equation? Ft is equal to Cd into half rho v square into area. Right? This is the equation. So now how to calculate CD? CD is equal to the what we call it as, this is a average drag coefficient. It is 1.328 divided by root of REN. Already we have calculated already this CD, that means the REL value. So if I substitute that 1.328 divided by root of 2,72,700. So if I put it the CD value, I will get basically some value. So this is 1. Then again, what is FD is equal to this 1.328 divided by 2,72,700. This is 1 multiplied by half into rho is what? 1000, because it is water. V is how much? 1.2 square. So this is rho V square by 2 into what? Area. What is the length of the plate and what is the width of the plate? This is this. So all this, if you do it, 0.3435 newtons. So if you want drag force on both sides of the plate, drag force on both sides of the plate. Right? So it is nothing but 2 times Ft. So 2 into 0.3435. It is equal to 0.687 newtons. The third problem is determine the thickness of boundary layer at the trailing edge of a smooth plate of length 4 meters and width 1.5 meters. The plate is moving at a velocity of 4 meters per second in stationary air. Kinematic viscosity of air is equal to 1.5 into 10 to the power of minus 5 meters square per second. Determine total drag on one side of the plate. Rho air is equal to 1.226 kg per meter cube. So again, for any problem, to know whether it is laminar boundary layer or turbulent boundary layer, only my solution is only Reynolds number. So what is Reynolds number at the trailing edge? So the Reynolds number at the trailing edge is equal to, it is VL by nu. V is given as 4 meters per second. Length of the plate is also given as 4. and this is given as 1.5 into 10 to the power of minus 5. So this answer will be 10.66 into 10 to the power of 5. So that means it is greater than 5 into 10 to the power of 5. So therefore, the boundary layer is turbulent boundary layer. So once turbulent boundary layer is formed, then for the sake of just finding out the even thickness also, then what is the formula for the turbulent boundary layer thickness? Delta by x is equal to, then it is 0.376 divided by REL to the power of 1 REX to the power of 1 by. If I want to determine at the trailing edge where x is equal to L, then delta by L is equal to 0.376 divided by REL to the power of 1 by 5. So 0.376 into L divided by REL to the power of 1 by 5. So if I put it 0.376 into L is 4 meters. REL is 10.66 into 10 to the power of 5 whole to the power of 1 by 5. Then it is coming to 92.1 mm. Next question he has asked is drag force on one side of the plate is asked. CD into half rho v square into area. So CD is equal to 0.074 divided by REL whole to the power of 5 because it is turbulent boundary layer. So this is 0.074 divided by 10.66 into 10 to the power of 5 whole to the power of 1 by 5. So it leads to 0.00488. This is CD value. Then what is FD is equal to CD value 0.00488 into half into rho v square. Rho is 8, so rho v square into area. Area is length of the plate into width of the plate. So if you do it, this is 0.2637 newtons. You see both combined how I will do it. It is required. Please read the problem carefully. It is required to determine the friction drag of a submarine. The length of the hull, that means the length of the submarine, is 75 meters and its surface area is 3000 meters square. Then critical Reynolds number. The meaning of critical Reynolds number is the Reynolds number at which the flow changes from laminar flow to turbulent flow. Critical Reynolds number at which the boundary layer changes from laminar boundary layer to turbulent boundary layer. Critical Reynolds number is 5 into 10 to the power of 5. At this Reynolds number, the boundary layer changes from laminar boundary layer to turbulent. Assuming the boundary layer at leading edge as laminar, leading edge, not trailing edge, as laminar, obtain the frictional drag and power required to propel the submarine at 5 meters per second. Take nu is equal to 1 into 10 to the power of minus 6 meters square per second, and rho is equal to 1000 kg per meter cube. The meaning is at the leading edge, it is basically laminar boundary layer, right? The boundary layer changes from laminar to turbulent at critical Reynolds number of this much. So obtain the frictional drag and power required. When I am calculating the frictional drag, I must be calculating on the entire plate. So what is REL? That is the first question for me. What is REL? REL means actually Reynolds number at the trailing edge. This is what is more important in the case of calculation of frictional drag. So what is REL? REL is equal to VL by nu. So what is V? He has given 5 meters per second. Length is 75 meters. Nu is equal to 1 into 10 to the power of minus 6. So 3.75 into 10 to the power of 8. That means at the trailing edge, the boundary layer is a turbulent boundary layer. But he mentioned at the leading edge, the boundary layer is laminar boundary layer. So that means the question says that there is laminar boundary layer and which is converted into turbulent boundary layer afterwards. So then actually how to calculate? In such a case, the friction drag is equal to friction drag is equal to FD is equal to CD into half rho V square into area. So CD is equal to, because it is laminar plus turbulent, both are there. So first one you write it as turbulent boundary layer first and then minus 1700 by REL. The first one is turbulent boundary layer equation. This is to account for the laminar boundary layer. So this formula you use it and use the REL value. REL already we have got it 3.75 into 10 to the power of 8. So substitute it and get the CD value. So it will be 1.422 into 10 to the power of minus 3. Once CD is obtained, then FD is nothing actually. It is 1.422 into 10 to the power of minus 3 into half into rho V square. Rho is water, so 1000 into rho V square into area is 3000. So this corresponds to 53.325 kilonewtons. Then he has asked us what is power required. The power required is nothing but actually FD into velocity. So that FD into velocity is equal to 53.325 into 5. So naturally this is in kilonewtons. So into velocity you have put it. So you are going to get indirectly kilonewton, kilowatts actually 625 kilowatts. So that completes.
Like, share and subscribe. Hit the bell icon for more updates.